Welcome to the next part of this tutorial series on creating your first DirectX 12 application in C++. In the last episode, we created the root signature, which is needed to create a pipeline. I also discussed a bit about what to do with the so-called input layout. I think we will hard code it into the pipeline since we will only be creating one pipeline. Since pipelines are something that you want several of, you would have to create separate root signatures and or maybe not, but you could create separate root signatures, and you could also create different input layouts. But since the pipeline wrapper is what binds these things together, we will get started on that in this episode. We did a wrapper for the root signature and everything worked out. Now we will create the wrapper for the pipeline state, as it's called. We will move it into our folder here, and we will do the usual namespace engine. And we will do the same here. This is also another interface of DirectX 12, so you know what we need to do by now. If not, you haven't really been watching anything I've done for the last 14 episodes or something. We will use the comp pointer ID 3D12 pipeline state, and we would like a possibility of creating a pipeline state that is default constructed, meaning that it doesn't need any state fill out. It can just be an empty class. Since we will be storing it on our renderer API, I think we should preface it with the YouTube API. We also want to store a root signature, which means that we need to include the root signature. These 12 root signature. And then we also need an array of shaders, because we will be creating a pipeline state that has two shaders. All right, and we will of course need a oh, did we forget in our last episode the release function? No, we actually did do the release function. Great stuff. We need a release function, and we need a destructor. We need a initialize method. And we created them. We want to call release. We want to call release on our root signature. We want to call release on our shaders whenever we release this. And we of course want to call reset on the pipeline state itself if it's set. Okay. Create pipeline state object. Maybe. Okay, we need a device as per usual. If you remember from our first episode, the device is like the virtual context on which the DirectX 12 API actually operates on. So we basically need the device for most things that aren't simple um, command list recordings. Okay, let's see. A graphics pipeline state only takes a pipeline state description and somewhere to store it. Wow, that is easy. Think again. This is the pipeline state. It contains several descriptions that are expanded upon, and it's fairly long. So let's create a pipeline state description here, and let's call our method here. It will return an H result as per always. So we will ask our device here to create the pipeline state. Maybe it's graphics pipeline state. Was it graphics pipeline state? Yeah, well, it's also a graphics pipeline state, so that's great. And we want to store it in IID, PPV, args, and get the address of this pointer. We want to pass out an error. YouTube just complained about something. Okay, well, whatever. We will pass out an error. Improperly terminated macro. We probably need another parenthesis here. Well, okay, it doesn't complain, but it won't do as we expect. So we need to fill out some information in terms of our pipeline state object. Let's just start at the top. I won't go over every detail, but as you can see here, we need a root signature. Okay, that's easy. We've created a wrapper for our root signature, and our root signature only takes a device. So we simply initialize our root signature. Right now, our root signature is predetermined. Let's see. The root signature object therefore we simply pass in our root signature.get. Great stuff. That was easy. We know that one. Okay. Then there's some structure here called shader bytecode. Well, it's a pointer to the shader bytecode and the bytecode length. And apparently we need to do it for something called VS. Wouldn't you know that it is actually short for vertex shader. So we need to set our vertex shader bytecode. Let's just agree that our first shader will be our vertex shader. We will initialize it with our path shaders, vertex shader HLSL, and we will pass it a shader type. Let's see, HLSL shader type of vertex shader. And we won't do that. We will actually initialize it here. But we initialize it but we want the bytecode. Well, in our shader object, we have the bytecode. We can simply create an inline function that returns the bytecode. Get byte blob instead, because it's actually not the bytecode. The bytecode is part of this data structure, but it also contains the size, so therefore we will name it like that. Now, you could argue that this is properly named as something else, but we don't care about that. Get the byte blob, and then we want the buffer pointer, and then of course we want to specify the length of the same thing. Therefore, we duplicate this, get buffer size. Great stuff. All right, what do we need? We need a pixel shader. Oh my god. We need a pixel shader. We do not have created, we do not have a pixel shader. We will create one. Let's call this PS HLSL. We still want the entry point of main. We want a void function. And we don't want Visual Studio to try to compile this, so therefore we will exclude it from the project. Okay, let's set up our pixel shader here. We simply change the type here, and we got our pixel shader. Okay. Pixel shader. Shader bytecode. Shaders. Oh, whoops. We need to set it in the second part of the array here. Shaders, get byte blob, get buffer pointer, and bytecode length. Get buffer size. Okay. Now we've told that this pipeline wants a vertex shader and a pixel shader. It doesn't need any of the other shaders, at least for our needs. We don't need a stream output buffer, so we can ignore that. We are not gonna pass out the information. We need a blend state description. Mm, something about a multi-sampling technique. No, we don't need that. Let's see. The other thing does also sound a bit uninteresting for us. Well, let's see. The default values are these. We disable everything. These do not matter. Okay. So basically, if we fill out those, blend state, alpha to coverage enable, let's set that to false. Blend state, we will not be working with the blending at all. Therefore, we set it to false. Then the blend state, render target, the first one, blend enable, false. Blend state, render target, the first one, logic of enable, false. So we have basically, whoops, enable, disable blending on this pipeline. It will simply overwrite. This should be fine. I'm unsure whether it wants to render target right mask, but I think it's probably fine. Okay. After the blend description, we need a sample mask. We're not using sampling, so you might have guessed it. We do not use blending, but we want to sample everything, meaning that even though we're not doing, excuse me, sampling itself, we want to handle every pixel by doing nothing to it. So the sampling mask is actually specified in a bit field. We will set this to every bit, and then we will do sample description, which will be initialized as always as our standard values of a count of 1 and no quality, since we're not going to use it. Okay, rasterize state. Oh, what is that? Okay, it relates to something about how we draw. It relates to something about how we draw stuff. So, rasterize state. Cull mode is the first one. No, fill mode. Fill mode. We will have the options of choosing solid or wireframe. We want to fill our objects with the wireframe, rather the solid fill mode, because we want solid objects. Let's do culling refers to which side of the triangle that we don't want to draw. If we do front face culling, front mode culling, we only do back. If we do that, we only do front facing triangles. We might do none. Maybe we start out with none actually, and then you can play around with what you need in your setup here. Then we do the rasterize state front counterclockwise. This relates to the drawing order, meaning left or clockwise or counterclockwise. So this means that the front-facing part of the triangle is drawn counterclockwise. We will not use that for now. Yeah, let's see. Do we have any standard values? Yeah, we do. Our standard values are actually solid and back mode culling, so we will do that. Front is counterclockwise. Our depth bias, we don't care. Depth clip enable. Let's see. What does that do? Yeah, we don't mind setting the clip function to clip depth, clip enable true. Okay, we will basically just follow the defaults. Multi-sample enable, no, no, no. And we will set this as a 0 initialized struct. So these will be automatically 0. These will be 0, 0. And conservative rasterization will be off. Okay. I think the rest is fine. Otherwise, we will probably get an error. Okay, that's the rasterized description state. The depth stencil state. Um, Let's see. We will initialize that as 0 because we will not do depth testing before we have any actual 3D output. Okay. Now we're getting to the input layout, which is a let's input layout. That's the one that I wanted to do a wrapper around. Let's see. We will wait a bit with that. We want to set the primitive topology. We will be doing triangles. We will do the number of render targets, node mask 0. That will be later on. Number of render targets 1. And we will do our format for our render target RTV formats. We will only set the first one. And what's the standard value of that for us? We will get a DirectX 12 error if we do not specify the correct one. Let's see, maybe we just go with the standard one. No, okay. Format, didn't we actually, oh, we specified it already. We specified it in our swap chain, let's see. Okay, this is our format. Okay, we don't even need to guess. Okay. Then there's the depth stencil view format, the sample description. Didn't we do that up here? Yeah, we did. Then we did the node mask, cached pipeline state. We don't do that. Then we can do flags. We won't be doing any flags. And I think actually that is it, except this input layout. The input layout is always something a bit tricky. You have to specify a input layout description here. Let's see, what does it contain? The number of elements. Right now we do not have any, and we need some kind of array here. Okay. We need a series of a pointer to D3D12 input element description element. It's plural, and we simply initialize them. We can't initialize them as 0. Let's see, DirectX 12 input layout. Can we get a good example of a input layout? Nope. Okay, if we we can't access that. Okay, here's an input layout. It's a shader semantic, as they're called. It's a name inside the shader, the input assembler slash vertex shader step that specifies what is this called in semantics in the HLSL shader language. We will, of course, discuss that. in a future episode whenever we do our shading. And what is, let's look up the actual struct here. The as you can see here, this text explains it, the semantic, the input slots, different stuff here. The format of the data structure is also specified. I just look up this. So the semantic name, the semantic index, is that the same? Yeah. The format of the data structure, the input slot of the data structure, which is usually 0, I think. The way the aligned byte offset, meaning that where inside our input structure do we need to offset to access this data structure. Be mindful of overlapping data structures. And the classification here. Per vertex data or per instance data, if you do instance drawing, you need to use some kind of handling of instance data. But we specify information for each vertex in this pipeline, meaning that we will be using that input classification. Lastly, the data step rate in terms of how many instance or vertices per instance is actually used. So if you're using the same data for several vertices in terms of instance drawing or derivatives of that methodology, yeah, you would manipulate this factor here. We will only do a simple input. So if we basically copy this, there's no need to write out this if we can just use that. Let's see. And of course we want to do a one here. And we do another encoding format. So this actually creates a data structure. Huh? Oh, it's the 12 one, but I don't think it changed. Maybe it's just like, let's see, DirectX 12. Whoops. There we go. And it's still the same information here. Okay. Yeah, we did the correct thing. Okay. The classification, let's see, blah, blah, blah. There we go. So we want this one. There we go. Let's just keep this like this. So we have the semantic called position. It's placed at semantic index 0, even though the example that we had earlier here is fine. Let's see. For the element, it's only needed where the elements have the same names, as you can see. You specify the format. Let's just return to that in a second. A number for the input assembler. and of course the bytes. So if we had two components, the aligned offset of the bytes would be passed in, I think, as this component here, and it would specify how large the structure is. This is um, a series of floating point numbers with 32 bits, 3 of them. So you can calculate how many bytes that is. It would be 12 bytes, meaning that the next semantic would have an offset of 12 bytes. So let's say that we want to use this input as our data. Maybe we actually want two kinds of input, a position and a color. So let's see, elements. Maybe we just want to point to the root. Yeah, okay. And we create another semantic here. Let's see, we create the color information. Let's see. And since semantics use captioned names, we do like, let's see, local variable is not initialized. So if I do something like this, let's see. Maybe we want double clamps here. Yeah. So our array elements here. Okay, back to this. There we go. There we go. So we would of course like a alpha value here. That is also 32 bits. As you might remember, the second to last component specifies the byte offset, 3 times 32 bits is the same as 3 times 4 bytes, meaning that we have an offset of 12. So now we have created a pipeline that takes in information in the input assembler that has a position consisting of 3 floating point numbers with 32 bits and a color that has 4 floating point numbers with 32 bits. Great stuff. Okay, we're about to test out if our pipeline state here actually will be created correctly. Let's see. And we did specify the shaders and so forth. So let's test it. So we could simply delete this because now it's encapsulated inside our root signature. We don't want this. We want actually to store a pipeline here on our render API. And it's part of the whole setup here. Let's see, pipeline state, base pipeline. Okay. And then in our initialization step here, we want to create a initialize function where we pass in our device here. And let's see how this works. We have an error creating the pipeline state. Let's see if we get any information from DirectX in terms of creating it. We do get our debug information here. pixel shader is not null. Okay, so actually this doesn't pertain to our pipeline itself, but it says that, well, you haven't provided us with a screen position in the rasterizing unit. What are you doing? We trusted you. We can't use this information. Okay, so this actually is helpful once you understand what it means. It means that we have some problem with our shader program. It said, the whole system said, fine, I'll create your pipeline, fine, I'll use those shaders, fine, I'll use that root signature. It's all fine and dandy, but you have enabled a rasterization unit. You expect to draw triangles, and the pixel shader is not null. So you need to pass me some basic information about where on the screen I should rasterize to, at least which pixels I should consider drawing. Um, and I want you to translate that position before the rasterization unit. Therefore, this relates to something in our vertex shader, because if you may remember the graphics pipeline here, the rasterization unit is before our uh, um, or rather, the vertex shader is before our rasterization unit, and it says that it wants it before the position is not provided by the last shader before the rasterization unit. Our last shader before the rasterization unit in this pipeline is our vertex shader. This is the power of the DirectX 12 debugging layer. If you have not implemented because you just wanted to skip ahead, you will never know what problems you have made for yourself in which areas of your program. So therefore, I highly recommend that you enable the debugging layer. Of course, if you're an expert and you know exactly what's going on every time, no matter what you're doing, don't enable the debug layer. Get a promotion wherever you are in this world. It sounds awesome, and I won't be able to do it myself. Let's just admit that. Anyway, so our vertex shader here needs to pass along something that the pipeline state can use, and I have a prior knowledge, so I happen to know what it expects to be input into the pixel shader and the rasterization step. Um, uh, I'm not sure what your question means. And hello on Twitch. I'm doing a YouTube exclusive, so I'm not that good at responding right now. Let's see. But anyway, the thing that the DirectX 11 or rather 12 rasterization step and vertex or a pixel shader step wants to have information about is the uh, calculated screen position, and it's given in a system semantic for the shader programs. These are system semantics, and you can always look them up. But SV position is related to the pixel location. The documentation here is not really clear on what it means, but um, um, if you've worked with DirectX 12, you learn to realize that the S underscore S, sorry, the SV position is related to the screen space positioning. So it can also be used for some other things depending on which shader it um, we're talking about. Okay, we will take a vertex shader output here and declare that. And we will pass out a float for position. And we will not initialize it, but we will give it the semantic SV position. I think we need to do like this. Yeah. So this is now supposed to return a output, but it doesn't right now. And we will create an output struct that is our struct that contains our position. If we compile this now, since we have a high or rather low tolerance for warnings, this will give us a warning and thereby a compilation error. So let's just initialize this. I'll go more in depth with shader language programming, but it's basically like any kind of programming language, and it's highly similar to C++ and C. So yeah, but now we've written a small vertex shader program that deliberately returns the SV position semantic to the next shader steps, which is our rasterization unit and then our pixel shader. So let's see if DirectX 12 now complains that we haven't provided the position. Well, it doesn't. Everything compiles, everything runs, we have no errors. So that was basically what it was trying to tell us. So once again, I advocate that you enable the debug layer. No, I won't show you an example of where the debug layer won't provide any information in case you don't enable it, because yeah, that's kind of pointless. Anyway, okay, I'll try to do the last steps of this episode rather quickly because I have to go in a short while. Let me just check. Yeah, I have to go in a short while. So let's create a data structure that actually mirrors our pipeline state, because we told the pipeline state that we expect this input for information. The problem is that well, I don't think that Microsoft has done any particular applications, but WPF is rendered in DirectX 9 or something, maybe even DirectX 10. So that's a basic example of an application that runs DirectX without being a game. So, but yeah, I won't create applications that are not games, because DirectX 12 is um, really game focused. I think there might be easier APIs to do applications that are not game related, at least. You could do 3D drawing models, but it will be basically the same as games, renderers, graphics editing programs, and so forth. Anyway, our input description here is related to these data structures here, and actually our vertex shader here will have a input that is passed along from the inputs merger input state here. So we know that it will get the float 3 data and the float 4 data when we the input assembler passes its data along. So we can create a variable here in the struct for our input that is called position, and we named it position. So therefore we couple the variable with our semantic. We also name this color. So we will give it our color. And remember, we specified the semantic here. So they are linked not only in terms of memory layout, but also in terms of the semantic. The shader expects this because we created a pipeline that is defined this way. Okay. As per any other method definition, we simply tell our program here, well, we get an input that has this structure here. Now we can simply swap our position. Maybe we want a float 3 as instead for our SV position, and therefore we simply copy our position here from our input. In the future we will do calculations on it. Maybe we want to pass the color along as well, so therefore we simply create a field that allows us to store our color. We then copy this data structure here inside our pixel shader, because we know that this pixel shader information will be passed in from the vertex shader output. And it will contain these semantics. And a pixel shader will also return a pixel color with an alpha value. So therefore, right now we will just return the color white. Now we will actually use the pixel shader input here and return the input.color. Since the SV position actually determines the pixel on the screen in terms of positioning, the color can just be passed along and it will draw whatever color to that pixel on the screen. The vertex shader translates the information in terms of through the rasterization unit, of course, into pixel coordinates. But yeah, let's see if everything compiles. Okay, we have a problem. What's our problem? Shader compilation error. Not all elements. Okay, we actually need a float 4. My bad. And we can do like this. Let's see. Yeah, so let's see, does that work? Okay, now we only have one error. And lastly, our return value here of the pixel shader is not correct. It warns us that the semantic is missing for this return value. Well, what is the return value? Or rather, what is the semantic for that return value? And we can again look into our system here. System variables, target, the output value that will be stored in a render target, The index indicates which of the 8 possibly bound render targets to write to. The value is available to all shaders. So we simply want our output semantic here to be bound to the target, and you don't need to specify the render target. Let's do naming here. That is as our convention, because it will just use the default one. Okay, what's our next problem? Our input signature parameter must be float 32 and must be XYCW. Okay, so it quickly knew that we weren't returning a float 4 instead as the appropriate semantic. Okay. Now we basically have a shader program that passes along the screen positioning and the color for our vertices. Great stuff. I think I won't be able to make it in terms of doing the actual draw calls. We are really close in terms of doing the draw calls. We actually just need to upload and bind the stuff together, and then we can do a draw call. But I think this episode has been fairly long, and yeah, since it's a small but relevant topic that I don't need to rush through, I will end the episode here. So we started doing shader programming without me even giving an introduction to that. It's not a real programming tutorial, so you might already know how to program shaders. Anyway, at least I hope I explained parts of where the pipeline state and the shader programming languages are bound together, and why the application fails whenever the programming shader programs doesn't fit the defined pipeline. It's because the shaders, the pipeline, the root signature are all parts of what takes data at the input assembler and outputs something to a render target and eventually to our screen. So they are intricately wound, and you need all objects and you need them to fit together, so to speak. All right, I think that is it for this episode here. Are there any questions? Otherwise, I'll end this episode. Well, it doesn't seem like it. Excuse me. Okay, I think we got a really long way. We're about to do our first draw calls in our next episode. There's literally only a few lines of code left, and we of course need to upload some data, but we will do that fairly quickly. Yeah, that was progress. If you have interest in me doing the actual 3D rendering in DirectX 12, let me know either in the comments or during the next stream/episode. If you have any wishes for future topics that this tutorial series should branch out into, let me know. for me, this takes time out of me working on my own project. So therefore, I will only be doing certain tutorials slash episodes in case there are high demand for it. I'll of course finish this up so that there are no loose ends, and you can at least do a bit of 3D rendering. Yeah, but I won't be doing any advanced or intermediate or even beyond beginner topics without a large enough interest. Since, yeah, I spend a lot of time on doing these episodes. Anyway, if you found this helpful, inspirational, or useful in any kind of way, maybe entertaining, even though I only make bad jokes, feel free to comment, like, or subscribe, or even support the channel. The GitHub repo will be updated, and you can always use the commit history to go back to earlier episodes and use different builds of this setup. Yeah. All right. Thanks for tuning in, either during the live stream or in the future. Stay well and have fun. Bye bye.